Good morning, good afternoon, and good evening, and welcome to the Friday Talk Show with your host Rajiv Kulkarni on Global Electronics Platform. Today is July 3rd, 2026. We have crossed already 6 months of this year, 2026, and entering into the July month, which is the seventh month of the year. And today is a kind of a holiday in the United States because July 4th is tomorrow, which falls on Saturday. So a lot of companies and a lot of establishments are closed today, celebrate the Independence Day of United States on July 4th, which is tomorrow. So global electronics consistent effort and also persistently following up to bring new and new topic every week to educate, to share the wealth of knowledge that is being carried by the veterans who come as guests on our platform. Global Electronics consistent effort to educate people in the electronics community, whether it can be related to the process engineering, design engineering, supply chain, or the market intelligence, and so on and so forth, considering the electronics manufacturing activities globally. Today's world, the global electronics manufacturing level has increased substantially due to the intense circuit designs, requirement of high power designs which are engaged in AI data center applications, which is growing exponentially in the global market. With that said, today's episode, which is a series of episodes, I would say, physics based HSIO interface design, episode number 5. Yes, this particular episode has been conducted, or I would say presented, by Mr. Ambaprasad, who is a veteran having more than 40 plus years in the design of PCB and also in the electronics manufacturing activities. So the title is Chip to System Level Packaging. Chip to System Level Packaging in AI Server. PCBs face multiphysics challenges that span electrical, thermal, and mechanical and material domains. As AI workloads push bandwidth beyond 1 terabyte per second and power densities above 1 kilowatt per board, designers must simultaneously solve signal integrity, heat dissipation, mechanical stress, and reliability issues across chiplets, interposers, and multilayer PCBs. So, ladies and gentlemen, let's welcome Mr. Ambaprasad, who is based out in Silicon Valley of India, which is Bangalore, in the southern state of India called Karnataka. So, Mr. Ambaprasad, good evening and welcome to the show, sir. How are you this evening?
Doing extremely good.
Very good, sir. And so I believe Bangalore is really getting more and more condensed with the growth of electronics industries globally, as well as a lot of investment is being carried out on the design side of it in Bangalore.
Yeah, what started in the 50s and 60s is now is an unbeaten run. And this never stopping.
It's
And
never
it got
stopping.
accelerated in 80s. A lot of OEMs and ODMs design houses are in Bangalore,
Uh-huh.
especially eastern part of Bangalore,
Uh-huh.
precise.
Very good, very good. Okay, so Mr. Amba Prasad, let's get on to our subject. Today's subject is chip to system level packaging on our series physics based HSIO interface design part 5. Let's continue
Full
from
size?
full size it is.
Small size.
Eh,
Go to full size.
no, it is full size only.
Okay. This is where we stopped our episode number 4.
Yeah.
Therein, we compared the design of Concorde and the design of a server PCB with high-speed interfaces is almost identical. This was projected by one particular author. I shared the links with you in the email. Maybe you can post it in the chat box. The book link I have already shared. Now,
Yeah.
physics-based interface routing, chip-level interfaces, chip-to-system packaging. So we started with the packaging earlier, the actual enclosure. We covered that, the difference between a telecom enclosure versus a AI enclosure. We did it. Now let's start from a chip. We go backwards. We start from a chip and we go towards the actual packaging, the rack. And here I'm telling chip to system level packaging, PCB implicit. The audience which are following us, most of them are designers and PCB designers. So I assume that PCB is a part of the game. I don't have to market PCBs myself because people sometimes complain. I always talk about PCBs sometimes. So they say don't do it. That's why I told it is implicit. PCB is taken for granted. Chip scaling, scale up, scale out, and scale across. This is a terminology especially used in data centers and servers. Distance versus data transfer speeds. This I never get tired of presenting because even as on June, three more new MSAs have come, especially to address AI backend packaging and the EMIR challenges, that is electromigration and IR drop. This is the actual challenge. We stop with that, and as we go next episode, we unravel one by one. Let's go to next page, please. This chart is publicly available from TSMC. If you look, it starts at 1987 and it projected up to 2028 as on now. But next year, they still 2028 may become 2030, like that. If you look at the node width, it was 3 microns somewhere in 1990. Then it started reducing 3 micron to 1.5, 1.21, and it became 0.18 micron in 1999, 0.13 in 2001. It goes, then 90 nanometer, 865 nanometer. This is the node width. It's going. Somewhere in 2025, 2 nanometer width is going to be achieved. And then afterwards, we are going to angstroms. This may or may not happen. And again, we cannot solve packaging by in silicon alone. Then we may have to go for a heterogeneous packaging. So that's the idea. Presently, a chip package is doing exactly the same job what a PC motherboard was doing, say, some 20 years back. So much of compute has gone into one chip actually. And this is achieved only through pure packaging efforts, nothing else. Next page, please. This is from IEEE 802.3. I have taken. This is also publicly available. Here they have made a task force to address AI backend packaging. They projected some schematics and some line diagrams and some schemes. This is how a data center network looks like. Uh, there can be some changes, but this is what IEEE is proposing. Then you have a back-end scale out, back-end scale up, and there is a front end. That is the Ethernet. All fibers will be at the front end, and back-end scale up and scale out. There is also what is called as scale across. So these are the three terminologies. Whoever works in server market and telecom market, they are conversant with this scale up, scale out, and scale across features. Next page, please. Explaining again here, what does scale up means? You increase the bandwidth, density is very critical, latency is extremely low, switches will be in layer 1, then media is generally copper. The interconnection is only through copper. Then you go to scale out, it is a very high bandwidth, density is very much important, latency is low, there can be 2-3 layers of switches, And again, you get into optical fibers. Scale across. Now, scale up will happen within the same rack. Scale out will happen within the same premises, maybe in the same data center white space. And scale across will happen across same premises, maybe what they call it the same cluster, two buildings, or it can happen in the same city, or it can happen across countries and continents. These are the three terminologies they use. Bandwidth is high, density is very important, latency is high, deep buffer switches, single mode fiber, and multi-mode fiber. They use all this. In fact, cabling and fiber becomes as important. It is a part of the connectivity. Next page, please. Here again, scale up, scale out, and scale across, especially with respect to cabling, we have shown cable included optical fiber cabling. Copper is used in scale up, 10 Tbps per GPU. Single mode, multi-mode, multi-core fibers. Then scale out, density and bandwidth will increase 800 Gbps. Today, most of the networking is happening in 800 Gbps in data centers. We are again showing what are the cables they are using. And scale across, it can be in the between two clusters within the city, or it can be across the continents. It is bandwidth latency. These are the terminologies they are using. These are the options available. I think we can stop at this and then go to next set of where we are explaining how cabling is done, and then go to the PCB level.
Okay, we can do that. I will take a quick break here and watch this quick video and we'll come back. Good morning, good afternoon, and good evening, and welcome to the Friday Talk Show with your host Rajiv Kulkarni on Global Electronics platform. And Global Electronics consistently brings every week, sometimes due to the conflict of travel plans and various activities, we may not be able to broadcast a live show. Sometimes we do some premiere show, and sometimes we just are not able to showcase anything, and the inconvenience is highly regretted, and we will try to make it more and more consistent shows as we move forward. Every topic is so different, and every topic brings a lot of wealth of knowledge from our veterans who have extensive knowledge in the electronics manufacturing activities. And today's topic is a series of topics that we have been conducting for the last 4 episodes, which is physics based HSIO interface design, and this is the part 5. And today's title is chip to system level packaging, with our host Mr. Ambaprasad, who comes from Bangalore, the Silicon Valley of India, and with a lot of wealth of knowledge in the electronics manufacturing, especially related to the PCB design sector. So let's welcome Mr. Ambaprasad again, and I will try to share the screen, and let's move forward, Mr. Ambaprasad. Here we go. So next page, here we go. Yeah, scaling AI networks, optics for scale up.
This slide I have taken from Ethernet Alliance, which is 20-year young alliance, like SMTA and IPC. These are also an alliance. They publish a lot of road mapping and again PDK, ADK, SDK. They are into that. Ethernet is the backbone of our communication. Optics for scale up, instead of CPU, we are talking of XPU. It can be a GPU also. Here, 72 device too many. So far, it was something like a 72 devices like that. Now it can be a thousands of devices can be clustered. Next page, we will show how it is done. Placing optical engines close to XPU and switch ASICs, example code package optics, uh, can expand the scale-up network, avoiding need for a megawatt racks. What you are doing in a rack level can be done in a 2U rack. MCF, that is multi-core fibers, can simplify deployment of these scale-up networks. 4K fibers for 512 port into 800G switch, or a 10K fibers at a NVL2 node. NVL2 node is a proprietary NVIDIA node. So there are a lot of, I said earlier, even last month, 3 new MSAs have come. This is never ending. Earlier, one MSA is to live for 5 years. But now it is MSAs, they are getting revised every 6 months. So that's the speed at which they are working. Go to next page, please. This is how a cabling happens. Here, a AI cluster of 32,768 GPUs have been interconnected to each other.
Wow, wow.
This is
This
amazing,
is
actually.
this is actually very very mind blowing, I would say.
Yeah, this is,
This is
I have shown there were 3 pictures were available. One of was a low end, one of them is a very high end, one of them is a middle one. This is the middle one I am showing. The low end, maybe people are already aware. I don't want to bore them. And by showing a very high end, I don't want to take it. People should not be taken aback. So that's why I thought somewhere we start in the middle is the best. Always in when we talk of telecom and data center, there is a reverse compatibility as well as a forward planning. They say you are future ready. You cannot be future proof. You are only future ready. That's why sometimes the installation may be over designed, but it is populated or scaled up. So this is from a cabling company. Again, from Ethernet Alliance, I have taken this. There are spine cards, leaf cards, and so many fibers. This is amazing. And the other
yeah,
challenge here is the thermal, which maybe we do it in somewhere in the next few episodes.
sessions. Yeah.
Yeah, we are running out of air cooling. Everything is liquid cooling.
I think thermal management is a very important topic these days, especially in the AI data center market space, you know. So, yeah, okay.
Next page, please. This is again IEEE 802.3 DG objectivities. They started a AI networking protocol program. They have their own number. Maybe next time I can share that. So here they are telling 200 Gbps, 400 Gbps, 800 Gbps, 1.2 TBs. And they're telling the signaling rate, then the backplane protocol, then copper cable, which cable has to use. Everything has got a numbering scheme, a single mode, multi-mode fibers, and the distance they are telling how much it can cover. 500 meters, 2 kilometers, 10 kilometers, 20 kilometers, 40 kilometers. 40 kilometer may look something very odd, but within a cluster, 40 kilometers is nothing.
Nothing,
Between
yeah.
2 data centers in the same cluster, 40 kilometers nothing from one rack to another rack in
Yeah,
another premises.
yeah.
These are the things. Next page, please. Here again, OIF forum have projected a very audacious plan, so to say. They are challenging Ethernet, challenging they are doing. In 1980s, it was 10 Mbps, 1990, 100 Mbps, 2000, 1 GB, that was when our Concord challenge started. The book was published and all. 10 Gbps at somewhere in 2022. Sorry, 2002, 2010, 100 Gbps, 2020, 1 TBS payload, 10 GB, 1.6 TB they are expecting in 2020. By 2030, 3.2 TBs they are expecting. This is what it is. But 2030, what they are projecting can happen by 2028. Always they have beaten their own records. It's like in IPL matches, every year we see some 50 runs are being added. Sometime it was 200 runs, now it is 250, is taken for granted. So like that, they are doing. So that's what it is. You cannot be future proof, you have to be future ready. Next
Okay.
page, please. This was 2026 Ethernet Alliance map. 3.2T they are showing by 2030. So these two, one by IEEE, one by Ethernet Alliance, they are more or less there in agreement. So these two, if we compare, they are more or less there in agreement. They are 2030. By 2028, they may project up to 2040. It's going on and on and on. These are again optical evolution. We covered some of this in the previous episode, but again here we
Yes.
are showing without optical, this connectivity is not possible. This is a part of the game. It is a part of the playbook. Co-package optics, onboard optics, pluggable optics. Pluggable optics are what it was earlier. Then it goes to onboard optics. Then optics will be merged with the package. That is the co-packaged optics. They are showing everything to use a retimer, yes or no. Retimer, if you use, it will enhance the distance, but it is thermally it is very difficult to manage. They get heated up like anything. Next page, please.
Wow. I
This
like this
is one of
slide.
the best slides I put my hands across. Here, like we compared a Concorde with a PCB. Here they are comparing an automotive with a PCB. They are showing what all you have to multi-physics. When I was telling multi-dimensional, multi-physics complexity, here they are telling again requirements, planning, and then configuration. This will happen for PCBs also. It will happen for automotive also. They are showing what all you have to do: data management, engineering management. Then if you go to electronics, it is electronic system simulation, analog and RF circuit, digital circuit, design for manufacturing. Now, when I say analog, RF, and digital, at when we started the PCBs 40 years back, there used to be two separate racks by itself. Then it
Yes.
became the same PCB. Now it can be the same package also. That's how it
Yeah.
is scaling up. Then device modeling, EM physical design, thermal management, electrical engineering, system simulation, thermal management, energy management. Then again, mechanical, this is a co-design. Uh, again, crash and safety testing in automotives. And here also, when we do packaging, the packages should not touch with each other, even in XY axis as well as in Z axis between two part slots. That is also called as a collision detection only. The industry calls as
Correct.
a collision detection. The PCB, what we designed may be very good signal integrity, power integrity, and say EMI, EMC. But if it cannot be inserted into the card cage properly, it becomes a very expensive showpiece in your company reception showcase. That is what it can do. It will be non-functional. So that's why mechanical verification becomes very much important. Design for excellence, design for DFM, which I am actively doing nowadays with a lot of clients. Then assembly process validation, where SMTA is done. We are doing it on a digital twin. Then service process validation, then manufacturing, then that's it. Yeah, they can be even the assembly up to assembly level. They are gone. They are gone to assembly, soldering, joining, cabling, everything they have shown. This is a very beautiful chart.
Excellent.
Next page, please.
Okay, I think we are done.
Now there is one more.
This one?
This is the one.
Yeah.
So this
Yeah.
is where it all meets. When we do, okay, this is a teaser for the next episode. Our next episode is based on this. So here, EMIR challenges and high density GPU socket seashore breakout regions. When I say seashore, we have a square package. There is a east, west, north, and south for a package. That is where our high-speed interfaces will reside, the pins. It is called as a seashore. The company calls it as a seashore. Some people call it as a beachfront. Even if you look at a PCB, say in the 80s and 90s, the connectors used to be at one end. That used to be at the back end, front end. And now the same concept is used in packages also. It is called as a, whenever we did a PCB routing in the 80s and 90s, only the experts used to do connector routing. It was a skill by itself. It was a science by itself. The same thing applies to a package. That's what I was telling. What a motherboard was doing in the 90s, a package is doing it now. Only the scaling has happened. So EMIR, that is electromigration and IR drop. Because of densification, power management, these two will happen. The gap between the vias is too less, gap between the traces and pads is too less. Though our design is correct and simulated properly, due to material issues and sometimes manufacturing defects or whatever, DFM not being done properly, analysis not being done properly, even a design is proper at the CAD level, but in the actual live board, when it is energized, this will lead to a lot of heating and failures. So this can be next topic.
Session, yeah.
From here we take onwards. I have slides ready already for that also.
No problem. We will present
So
that
we
probably
can
next week.
go
Yeah.
ahead. And
Yeah.
this is, I told earlier, your signal integrity, power integrity is a soft issue. EMIMC is some sort of a semi-soft. It is neither soft nor hard.
Yeah.
But mechanical failure and EMIR failure is a physical issue. It is a hard issue, and
Right.
it will be realized only when the board is assembled. Unless we do
Right.
simulation properly and catch up this in DFM runs, it becomes a very costly mistake.
Yep. Yep. Okay, so with that, Mr. Ambaprasad, we really appreciate your continuous support in giving, in sharing your wealth of knowledge in the electronics industries, manufacturing, as we say. And as viewers are supporting us every week, and we request you to support us this way, and also share our link, the channel link, with your colleagues, with your friends who work in the electronics community, because that is the whole idea of Global Electronics, bringing you this show every week to share our wealth of knowledge in the electronics manufacturing. So series continues next week again with Mr. Ambaprasad, and today's topic was chip to system level packaging. With that, this is your host Rajiv Kulkarni signing off from today's episode, which is 3rd of July 2026, and the people who are watching in the United States, wishing you all a very happy 4th of July, and we will see you next week at the same time. Thank you, Mr. Ambaprasad, once again. We'll see you next week. And
1 minute. It is, we talked about 20 years for Ethernet Alliance, 30 years for somebody, 60 years for IPC, 44 years for SMTA, 75 years for India. USA is 250 years.
That is correct. 250th Independence Day tomorrow is being celebrated by the United States people and all over the world, who and we from Global Electronics wishing all the best and best wishes and happy 4th of July. With that, your host Rajiv Kulkarni will sign off for today's episode, and please take care of your health and God bless. Thank you very much.
Thanks.